بسم الله الرحمن الرحيم. نحاول اليوم انه نستخدم ال Abaqus wireframe model, two-dimensional model, to simulate حتى نمثل the portal frame indicated in the figure. Okay. The first step is to run the Abaqus or launch the Abaqus software. Okay. Then to start the drawing process, give an indicative name for the part, in this case portal frame seems adequate. Select 2D planar, select wire, and then to select the dimensions. In this example we will adopt millimeter, therefore our dimension will be in the range of 7,000 millimeter. So let us say 10,000. Continue. Start the drawing process. Okay, this would be the column pedestal. The dimension of column pedestal is 1 meter, and the steel is 4 meter. So we have 1 meter, okay. Then we start to draw the steel column. We have 4 meter, okay. Delete the dimension, then okay, then replicate the beam and pedestal, the column and pedestal, okay. Two with 7,000. Finally we will draw the girder. Okay, we will draw the girder. Check the length of the girder. Okay, we have 7 meter. Then done, press done to finalize the drawing process. The second step is to define the property. The property start with definition of material. From material we will have concrete. For pedestal, units, adopted units, include Newton millimeter. General density is not needed in this case because the problem neglect the self weight of the portal frame. Therefore density is not necessary in this case. We will have elastic parameters. Young modulus. According to ACI, Young modulus for concrete is equal to 4,700 times the square root of the compressive strength. Let us assume that 28 megapascal for compressive strength. That is mean we have a Young modulus in the range of about 25,000 megapascal. We have about 25,000. A Poisson ratio according to Arthur Nelson for concrete is in the range of 0.2. Press OK. The second material would be steel for columns and the girder. Units as for concrete, units are in Newton for force and millimeter for length. Mechanical properties. Young modulus هو 2000 2000 megapascal. Okay, we'll pass a ratio in the range of 0.3. The third step is to define the section for beams and columns according to Abaqus. Should start with the create a profile. We have we have firstly we have beam, we have column. Profile. Okay, this may be written to be maybe written as in the original problem, may be written as HEA 300. HEA 300. Okay, the dimension would be would be 360 for overall depth, 180 to locate the neutral axis, 170 the width of the upper flange, and 170 the width of lower flange. T1 13 millimeter as a width for the lower flange, and T2 13 millimeter also as the thickness of the lower and upper flange. And finally we have 8 millimeter thickness for the web flange. By the way, this were the dimensions of beam. Therefore, this name should be changed to IBE 360 profile for beam. Okay. Create HEA 300 profile for the column. Here we have 290 millimeter overall depth, and we have 145 to locate the neutral axis, to locate the mid height of the column. We have 300 millimeter for the width of the upper flange, 300 millimeter for the width of the lower flange, and 14 millimeter thickness of a flange. And finally we have 9 mm thickness of the web. Okay, now this profile, these profiles will be merged with the material to have sections, create sections, create section, beam section. Beam in Abaqus here means a frame in general. That is mean can simulate the axial shear and the flexural stiffness of the bar element. So here we have a frame according to the traditional literature and textbook. Okay, so we have girder section. Girder will be simulated as a beam. That is mean we will include the flexure, axial and shear stiffness in general. We will select IPE profile and material steel. Okay, the second section will be steel column section. Okay, will be simulated as beam also. We have HEA 300 profile with a steel material. Okay, now assign the section. We can automatically generate set also. We have steel columns, select steel. Okay, we have girder, select girder. Okay, finally we should define the profile and section for the concrete pedestal. Return to profile, pedestal, profile. We have rectangular shape. We have rectangular shape with dimensions of 600 millimeter by 600 millimeter. So we have 600 millimeter by 600 millimeter. Okay, then define the section. Pedestal section beam. Okay, we select pedestal profile with concrete. Finally define pedestal set and assign the section to the pedestal. Finally, we should define the coordinate, local coordinate. We will accept the default definition. To check to see if the default definition is appropriate in this case, part display option, select render beam profile, apply, rotate the section. Okay, the local axis and local location have been defined appropriately because they are located such that the applied load will produce bending moment about the major axis as in the problem description. Okay. The third step is to add the instant. We have one instant only. Add an instant to the assembly. The fourth step is to define loading step. We have initial step for boundary condition automatically generated. We will define applied load step, general, static general, continue. Here we will neglect the effect of geometric nonlinearity, so we have off for NL, nonlinear geometry. Increment, as we deal with a linear elastic structure, therefore the load can be applied, the total load can be applied within a single step. No load increment is necessary here. Okay. Interaction, we have no interaction in this case, as all members including girder, columns, pedestals have been drawn within the same part, therefore they are automatically rigidly connected to each other by the Abaqus software. We have no need for the interaction. Finally, load. Okay, finally load. Let us start with initial. According to problem statement, assume hinge supports to simulate the indicated separate footings. That is mean separate footings, the indicated separate footings here. These separate footings will be simulated as hinge support. This assumption is suitable when the dimensions of separate footing are relatively small, and when the underneath soil is relatively compressible. Okay. We have boundary condition hinges. Okay, select this point and this point, done. Reset rand U1 and U2. As we start with two-dimensional model, so we have definition for displacement in Y and X, and we have no meaning for displacement along Z, as this displacement is related to a three-dimensional simulation, and here we have two-dimensional simulation. And finally we have a meaning for rotation about Z U3, but we have no rotation about X and Y, as they are related to three-dimensional simulation. Here, as we intend to simulate the separate footing as hinges, U3 will be neglected. Okay. Applied load. We have point load, concentrated load, point load. We have no point to assign the load, therefore we should return to part and create a partition, face sketch. Okay, select this edge. We have by default we have 50%, that is mean the partition point will be located at mid span. Create partition. Okay, now return to load, applied load, point load, select the point. The value for point load as indicated in the problem statement is 100 kilonewton. We have 100 kilonewton. In CF2 we have minus to locate downward, 100 A to 3 to be in the Newton. Okay, finally mesh. Suitable mesh can be adopted here. Actually, as we have concentrated load only, even coarse mesh will be sufficient in this case. Okay, mesh cannot be assigned in the assemblage as independent part instance have been adopted. Turn to part. Okay, we will adopt 205 millimeter. Apply, create mesh, create mesh, mesh. Okay, finally go to define the job. Portal frame job, submit. Okay, the step 1 analysis of step 1 has been achieved, and we can review the results. This is the deflected shape. Okay, this is the deformation vector to see the deflection in vertical direction. Okay, we have deflection at mid span in the range of 11.65 millimeter, 11.651 millimeter. Unfortunately, we have no value from SAP to compare with. Okay, now we should return to modeling stage and go to output, field output, and we should go to select section force and moment and resubmit the job to determine the bending moment and shear force. Resubmit. Results. We can now have SM bending moment, section moment at integration point, section moment at integration point. Compare the value with the SAP. At mid-span we have 113. here we have bending moment. To be compatible with what we have from SAP, okay, we will change the legend for legend formulation from viewport annotation option. Go to legend and change the format from fixed to engineering. Okay, the positive moment would be in the range of 107 kilonewton meter. From SAP here we have 113. Okay, in the negative region we have about 59.4. Unfortunately, we have no corresponding value from the SAP to compare. By the way, the deflection from the SAP is indicated here. We can compare the deflection. Go to displacement and select U2. We have 11.65 millimeter. Okay, we have 11.23 millimeter. As expected, the deflection is or would be more closer between two models, as it depends on the approximation in function, while the discrepancy and moments are expected to be larger, as it depends on the second derivative of the function. In general, it is more simple to approximate the function itself, but relatively more difficult to function or to approximate or to capture the second derivative of the function. Thank you very much for your listening.